Baum-Welch reestimation, this is the learning problem. Given a large string of outputs, sequence of outputs, the goal is to apply the EM algorithm to learn the transition probabilities and emission probabilities and the initial probability of the HMM. Before we go over to the Baum-Welch algorithm, let's establish a color convention. So any box that's filled with yellow implies a probability condition. So it's the condition of a conditional probability. Now let's establish two rules that would be very useful in the derivations that will follow. So we are given a joint probability PMN, and M is from 1 through M, N is from 1 through N. As an example, the first event could be the roll of a die, and so M is 6 here, this is 6. And the second event here could be the drawing of a card, since there are 52 cards here, so this would be 52. Oops, I can barely write 52. Anyways, so the joint probabilities are given to us somehow. And our goal is to find P of M or P of N. How do we do that? It's very simple. P of M is we simply sum PMN over all possible N's. So there will be 52 possibilities here. We simply sum them up, and by the additional rule of probability, that becomes equal to probability of M, where M is maybe one outcome of the rolling of a die. Likewise, Pn equals summation M PMN. So remember this rule. What we are doing is, in order to eliminate one index, we are trying to eliminate M here, and we're trying to eliminate index M here. What we do is we sum the joint probability with respect to that index. And that gives us the probability with that index eliminated. That's rule number 1. Rule number 2, again, similar situation. And we are given joint probabilities of M and N. And M is maybe the roll of a die, so 6 outcomes, and N is the drawing of a card, so 52 outcomes. And obviously, summation M, summation N, PMN equals 1. Now suppose we do this experiment T number of times, where T is very large, maybe 1,000,000 times. What we do is each time we roll a die and draw a card. Again, we replace, and again roll a die and draw a card. And we keep repeating this experiment T times. And each time 1 out of M by N possibilities occur naturally. How many possibilities are there? 6 times 52. Out of which 1 will take place. Now, how many number of times the joint event Mn occurs? We are only interested in Mn when we have carried out the experiment T number of times. The answer is simple. The expected number of times Mn would have occurred is T times Pmn. Simple. And this is another rule that we shall be using in our derivation. Now let's go over and formally begin the Baum-Welch reestimation algorithm. So the learning problem is as follows. The number of states S is known. All the states are known. All the output symbols are known. And what's given to us is a output sequence or multiple output sequences. Just one single output sequence is fine, and it must be large enough. So T must be very large, very high in comparison to the number of states and the number of outputs, because we're going to learn all the probabilities. And the goal is to find a max likelihood estimate of the HMM theta star, which is equal to argmax with respect to theta of P, V, the string V of outputs, the sequence of outputs rather, given theta. And theta star is equal to P star, Q star, pi star. P is the matrix of state transition probabilities, Q is the emission probability matrix, and pi is the initial probability vector. And our approach will be to use the EM algorithm. So we've seen alpha Ti. Alpha Ti is defined as the probability of the symbols, output symbols, past and present, and the present state being Si. What if I multiply alpha Ti with the transition probability Pij? So Pij is the probability of transitioning from state I, which the HMM is in, to state Sj in the next time step. So that's alpha Ti Pij, and that's equal to this probability. Now I'm accounting for this St plus 1 equals Sj. So alpha Ti Pij is the joint probability of the output sequence V1 through T, and St equals Si, St plus 1 equals Sj, two consecutive states at times T and T plus 1 being Si and Sj. Now I multiply that with the emission probability Qj Vt plus 1. So at T plus 1, the HMM is in state J, and this Qj Vt plus 1 is the emission probability of emitting Vt plus 1 symbol from state J, and so this is equal to, the product is equal to probability of V1 through T plus 1 now. 1 through T had been taken into account already. V1 through T was accounted for, and now because of this I include T plus 1. So it's V1 through T plus 1, and St equals Si, St plus 1 equals Sj. Okay, so now before doing anything more with this, let's look at beta. Beta Ti is the probability of the future symbols if we are at present in step T and the state is Si, then beta is the probability of the future sequence given the present state is Si. So this is the future sequence, and this is the condition. The current state is Si is the condition, that's why it's colored in yellow. Following the same definition, beta T plus 1 is the probability of being at time T plus 1 in state J and the future sequence Vt plus 2 to Vt. So this is the expression for beta T plus 1j. Symbols V of T plus 2 to T given the state at time T plus 1 equals Sj. What if I multiply what we saw earlier was alpha Ti Pij Qj Vt plus 1, and graphically I've shown it here, and that's this probability here. And I multiply this with beta T plus 1j. What do I get? First, when I multiply it, I'm taking these conditions into account. So this product already had V1 through T plus 1, this green block here, and it also had ST equals Si and ST plus 1 equals Sj as part of its conditional probability. So when I take the product of this alpha Ti, Pij, Qj, Vt plus 1 and beta T plus 1j, this is what I get. Let's see how. I have, as part of my joint probability, the output sequence 1 through T plus 1 and then T plus 2 to uppercase T. So I combine, that gives me V1 through T, that's the entire output sequence. I have St equals Si here, and that can be incorporated down here. I have St plus 1 equals Sj here, and this is condition probability of St plus 1 equals Sj, and so from Bayes' rule, that gives me another joint condition, another joint event, St plus 1 equals Sj. So this is what I have. The product alpha Ti, Pij, Qj, Vt plus 1, beta T plus 1j is equal to the probability of the entire output vector given the consecutive states at time t and t plus 1 being Si and Sj. Okay, so this is what I wrote here. The same product, alpha Ti, Pij, Qjv, T plus 1 and beta T plus 1, and that's given by this probability. Now, I want to eliminate Si and Sj. What do? I do the summations. In fact, since I want to eliminate two indexes, I do a double summation. I sum over I and j. And what do I get? I eliminate from my joint probability, I eliminate St equals Si, and I also eliminate St plus 1 equals Sj. What remains is P of V. So I obtain the probability of V. So this is, by definition, this product alpha Ti, Pij, Qj, Vt plus 1, beta T plus 1, I denote as Zeta Tij. So the definition of Zeta Tij is the probability of the current state being Si and the very next time step being at state Sj given the entire vector V. Now this conditional probability can be expressed using Bayes' rule as the joint probability of St equals Si, St plus 1 equals Sj, and V, the joint probability divided by the probability of V, which is equal to this. How? Because the numerator here of Zeta Ti is this product, and the denominator, so this is the numerator, and the denominator is this double summation, which is PV. So Zeta Tij is defined. This is the definition of Zeta Tij. So once again, Zeta Tij is the probability of being in Si and Sj consecutive states, Si and Sj at times t and t plus 1, given that the output sequence is this vector V. And that can be obtained readily from alphas and betas and the transition probabilities Q's and P's. So this is graphically what zeta Tij is, and since it's conditioned upon the entire output sequence, I have shown that in yellow colored box. Now let's define gamma Ti. What if I sum zeta Tij over this j? I will eliminate j. This is the summation that I carried out over. And so that would eliminate this st plus 1 equals sj. And so that gives me simply probability of st equals si given output sequence. And that's defined as gamma Ti. Now we had used gamma Ti earlier during the matching problem. Anyway, so let's see, zeta Tij and gamma Ti. Zeta Tij is defined in this manner: probability of st equals si, st plus 1 equals sj, two consecutive states being si and sj at time t and t plus 1, given the output v. And it can be obtained readily from alpha, beta, and the transition probabilities p's and q's using this expression. Gamma Ti is defined as probability of this current state being si, st equals si, given v. And that can be obtained readily from the zeta Tijs. There is another way to obtain gamma Ti also. And you can refer back to the slide on beta V algorithm. So now zeta Tij is defined as probability of st equals si, st plus 1 equals sj, given v. If I add all the zeta Tijs from t equals 1 through t equals t minus 1, then I get the total number of transitions given v. Now, why t minus 1? Because I cannot define zeta uppercase Tij. Zeta for this t cannot be defined because there is no next state t plus 1. And besides, we're looking at transitions. So if I'm transitioning from state I to Sj, then I must have a few, if I'm here at time step t, then there must be a future t plus 1. So then there won't be any transitions from the last time step uppercase t. That's why I have summation from t equals 1 through t plus 1 here. Gamma Ti is the probability of being in state St equals Si given V. Now what's the expected number of times the HMM would have visited that state Si during the entire sequence at any time step until t minus 1? What I can do is I can simply sum the gamma Ti's. St can be anything. It can be 1 or 2 or 3. So I sum all of them, and that gives me the expected number of times the HMM would have been in state I, Si, between time 1 and time t minus 1. And the expected number of times until t, the expected number of times the HMM would have been in the same state until time t is, we can do the summation from t equals 1 through uppercase T. The difference is t minus 1, and here it's t. Now I told you that zeta Tij cannot be defined at time t. Nevertheless, gamma Ti can be devised in two ways. It can be devised from these zeta Ijs, as we just saw before. Another way to find gamma ti is by using the product of the alpha beta divided by the double summations of the alpha beta. I will refer you to the past slide to look at that expression. So zeta Tij cannot be defined at time step uppercase T, but gamma Ti can actually be computed using the alternate equation at time step T. So the expected number of times the HMM would be at state Si all the way from time step 1 until time step T is equal to summation 1 through T of gamma Ti. Frequency, that is the expected number of times the HMM would be at the initial state Si, is by plugging in 1 here, gamma 1i, t equals 1. By definition, that's the frequency of the initial state, Si given V. And the number of times in Si and observing output Vk given V is given by, now we have the gamma Ti's for each time step I, and so we have a gamma Ti here, another gamma Ti here, another gamma Ti here, another gamma Ti here, another gamma Ti here. We have different, for each time step we have a different value of gamma Ti. And suppose we observed this output Vk here, here, and here, 3 places. Then if we sum gamma Ti only for these places, then we get the expected number of times in Si and observing output Vk given V. So with these we get the E step of our EM algorithm. Expected number of transitions from Si to Sj is zeta Tij summed over t equals 1 through t minus 1. Expected number of times at Si until time step t minus 1 is summation of gamma Ti from t through t minus 1. Expected number of times at Si until time t, I have not written until time t, but it's implicit, given V is summation t equals 1 through uppercase T gamma Ti, and note that gamma can be obtained not only using the zetas but also directly from the alphas and betas. There are 2 ways to obtain gamma. The frequency of initial state Si given V is gamma 1i, and the expected number of times in state Si and observing output Vk given the output sequence V is summation of t equals 1 through t and only when Vt equals Vk. Only for the time steps Vk was the output of gamma Ti. So that's the E step of the EM algorithm. So from those expectations that we just obtained during the E step, let's try to estimate the probabilities. The transition probability Pij is by definition the probability of jumping to state J given the state is Si. And so that's given by this ratio. It's equal to the number of transitions from Si to Sj divided by the number of times the HMM was in state Si. And since these transitions can happen only until time step t minus 1, so here you'll have to consider that. And so this is the expected number of times the HMM was in state Si until time t minus 1, not until t. And that's given by this expression here. Summation t equals 1 through t minus 1 of zeta Tij divided by summation t equals 1 through t minus 1 gamma Ti. Emission probability Qik. That's equal, by definition, the probability of emitting output Vk given the state is Si. And so that's obtained using this expression here. The numerator is the number of times the HMM was in state Si and output Vk was observed, divided by the number of times the HMM was in state Si, which is equal to summation t equals 1 through uppercase T. Now we have uppercase T here instead of t minus 1, summation, and over all the times the output was Vk of gamma Ti divided by summation t equals 1 through t gamma Ti. And the initial frequency, initial probability of each state can be obtained directly as pi I hat equals gamma 1I. And this is a little paradoxical because we only have one large long string V that goes on for a long time, and somehow we're able to find the probabilities of the initial state even though we have one string, so it could have started from only one initial state. But we still can paradoxically obtain it because we have so much other information, all the transition probabilities and the emission probabilities. So this brings us to the M step of the EM algorithm. For each state I, we find the initial probability, and we get Pij, the transition probabilities, used for each states I and j as the ratio shown here, which we saw earlier, and Qik is also obtained for each I, state I, and output k, using this expression which we saw earlier. And that's the M step of the EM algorithm. Combining them, we have the E step and the M step. We initialize in an intelligent manner because the EM algorithm is very slow, so we have to intelligently initialize P's, Q's, and Pi's. And then we begin the E step. We have to run the forward algorithm and the backward algorithm to find the alphas and betas, whence we determine gamma Tij and zeta Tij. That's the E step. I haven't shown the expected values, but you can directly get them from here. And pi I is gamma 1I. Pij is obtained from this ratio for all values of I and j. Qik is then again re-estimated using this expression for all states I and output symbols k. And so these are the new estimates of pi qk, and we let p be equal to the new estimate, q be equal to the new estimate, and pi be equal to the new estimate, and then we go back to the E step, and rerun our forward and backward algorithm using the new values of p, q, and pi, and we carry out this process EM several times until convergence. One warning when dealing with hidden Markov models: you will be dealing with the probability, a product of too many probabilities. And the best way to approach this is, because it may cause numerical underflow, so these are always routinely handled in HMM-based algorithms using log probabilities. You store log probabilities, and instead of the products, you have log probabilities and you add them up together. Only when addition is required do you actually go ahead and take the inverse log and then do the multiplication. But right away, right after taking, you add them up, you again take the log. So always handle logs. I mean, always use logs. The end.